Hey there, and welcome to your final lesson on further mathematics algebra, um, which will be looking at simultaneous equations. So, um, you are probably already familiar with simultaneous equations from regular GCSE syllabus. This lesson will assume that you're very comfortable with the basic techniques of using elimination and substitution to solve a pair of simultaneous equations of two variables, either linear or perhaps including a non-linear equation. So if you don't have that understanding, you might want to brush up on that first to make sure that you'll be able to follow this lesson. Otherwise, let's get going. So first of all, we'll just do a quick recap of like the graphical interpretation of equations and in particularly simultaneous equations. We'll look at some non-linear systems, which some harder problems you might encounter, which is still technically kind of part of the regular GCSE syllabus, but features more prominently in further GCSE math. And then we're going to be looking at systems of three variables, with three equations, and applications of those, which is stuff that is a lot specific to further GCSE math that you wouldn't encounter at regular GCSE. So that's the plan for today's lesson. So quickly, what the graphical interpretation is. So let's say if we take a graph like this of a quadratic, what does that graph actually represent? Well, it basically represents all the solutions to that equation, all the coordinate pairs of like x and y, um, such that that equation will be true. If you substitute in the x and y, the left hand side will equal the right hand side. So all these points here, if you substitute that into these, substitute them into this equation, you find the left hand side won't equal the right hand side. But if you take all these points that are on the line, you see the equation will hold true. So that's basically what a graph represents. It allows us to see all the potential solutions of this equation. And so if we now draw another equation like this, so a little linear one, and we're trying to now solve these equations simultaneously, what we're trying to do is we're trying to find the pair of x and y values such that these two equations are simultaneously true, which you might be able to guess is going to be where they intersect. That those are the coordinates that are basically on both lines at the same time. And so they're going to be the pair of x and y values such that both of these equations are true at the same time. So if we were to solve this system of equations, it will basically find us these two coordinates. So that's what the graphical interpretation is for solving simultaneous equations. So let's look at some nonlinear equations as well. So say if we're just sketching this very roughly on a set of axes like this. So the basic case of, two linear equations like this, you should already be very familiar with elimination or substitution. We can find that one coordinate that they intersect. But you could get nonlinear case like this, where you've got a quadratic and a linear equation. So one of the equations will always be linear. If you had two nonlinear equations, that basically takes us beyond GCSE level now because it becomes a bit more complicated. But as long as one of the equations are linear, it makes the solution relatively straightforward. So here's one example with a quadratic and a linear equation. You could also have something like this, like a circle and a linear equation. So you should be familiar with circles as graphs. The equation of a circle, x squared plus y squared equals the radius squared. And you see generally you're going to get two solutions again. We can also encounter situations like this, where you see it's similar to a circle, but it's the x squared is multiplied by some number a, y squared is multiplied by the number b, and what that produces is essentially an ellipse. You don't need to be aware of that, um, how to use an ellipse like on a graph, but that's basically what an equation like this would look like, and we would be expected to solve simultaneous equations like this, but we can solve it in very much the same way as a circle. We can even go one step further and produce like a hyperbola like this, which again, you look at the equation of hyperbola, it's very similar to the ellipse, but instead of doing ax squared plus by squared, we have a subtraction and it produces a graph like this. Again, you don't need to be familiar with this graph, but we would be expected to solve those equations, which we can do in a very similar way again. And you see generally it will produce two solutions, but that's not always the case. So you could get something like this, the typical case where you get two solutions, yeah, with a quadratic and a linear equation here. But you can get something like this, where if you only get one solution, it's indicative that that linear equation is essentially a tangent to the quadratic here. So you only get one solution. And you can even get something like this, where, remember, the intersections of the graphs are the solutions to the system of equations. So if you get something like this, what this is saying is there are no solutions. There is no point where these two graphs intersect. And so what you'll do, if you try to solve that system of equations, what you'll find is you'll get something nonsensical. Maybe it will like reduce down to like 5 equals 10, which is obviously false. In which case, if something like that happens, that what that's indicating is that there are no solutions. So we need to be aware of that. Um, so the final case, something that's going to be new to you guys, would be something like this. Now, don't let this 3D graph here scare you. So I'm putting that there just to help you interpret what's going on with when we have like this system of equations here in the bottom left, where we have three equations with three variables. So when we've got three variables, you're essentially working in 3 dimensions now. And each equation, rather than representing a line, actually represents a surface. And you see here in this diagram, we've got three surfaces here, like a red, a green, and a blue. And the solution to this system of equations is essentially that blue point in the middle where all three surfaces intersect at the same time. So it's a similar idea going on here. Rather than dealing with lines, we're dealing with surfaces. You don't need to understand this graphical interpretation. I'm just putting it there for your own interest or help you understand. Like, you see how it's kind of doing the same thing, but just in a higher dimension. But what we do need to do, we need to know how to do, is when given a system of equations like that, three equations, three variables, we will need to know how to solve that to find out what x, y, and z are. But when dealing with three equations, you'll only ever get the linear case, like something like this, where you see there's no powers or anything like that. And that that produces something like this, where you see these surfaces are flat; they're not curved in any way; they're just flat surfaces. Just like how a linear equation of two variables produces a straight line, with three variables, it produces a flat surface rather than a curved one. So there we go. So that's kind of like the way to interpret all of this, how to sort of visualize it. Let's look at solving some nonlinear equations now. So I'm going to brush through this relatively quickly because this is still technically part of regular GCSE math, and I want to focus more on the further math. But some of the more advanced aspects you will encounter more at further math than regular GCSE math. So say if we take something like this, how do we solve this? Well, when you're dealing with nonlinear equations, generally the elimination method is not really going to work so well. What we want to do is use substitution, which is something we can always do here, because you'll only ever get asked something like this where one of the equations is nonlinear and the other one is linear. And if it's linear, then it's very easy to make one variable the subject. In this case, we've already got one as the subject. We've got y equals 3x minus 1. Y is the subject there. We've got y as an expression of x, 3x minus 1. So what we can do is we can take that expression of x and substitute it wherever we see a y in the other equation. So we'll essentially get this. So you see that y squared? It's 3x minus 1 squared. And you see what we've produced now is essentially an equation of one variable. So it essentially does the same thing as an elimination. When we substitute, we're essentially eliminating one of the variables to produce an equation of one variable, which we can now solve. So if we expand this out, so 3x minus 1 squared, we expand that out, and then we multiply through by the 2, collect together like terms, you'll get a quadratic equation like this. So you might want to pause here and try this for yourself. Expand, simplify, collect like terms, basic algebra techniques that you should be familiar with. And then once we get to this, well, first of all, we can simplify this by dividing through by 3. There's a common factor of 3 there. But you see what we've got now is a quadratic. So we now need to solve that quadratic in any way you see fit. You could use, quadratic formula, or perhaps this could be factorized, who knows. I've got the solution here of x being equal to 2/7 plus or minus 9/7. So we could work out what those two values are. If I add 9/7, I get the minus 1, no, no, the 11 over 7, sorry. If I subtract 9 over 7, you get the minus 1. Well, now we just need to substitute that back into one of the equations that we started off with. Typically, you want to substitute into the linear one because it's just a lot easier. So you can use either one, it will work because they both have, by definition, simultaneous equations. They're going to have the same, values at those points where they're intersecting. So you can substitute into either one. You might as well pick the linear one because it'll be easier. And you find the corresponding y values. And you need to make sure you pair them up correctly now. So we produced that 26 over 7 for y from the 11 over 7 for x. So those two come together. And the minus 4 came from the minus 1. So make sure you pair those up correctly. Because otherwise you'll get something like this happening. So you might have recognized from the start that non-linear equation we've got is basically an ellipse. The first one is just a linear, straight line. And you see we get our two solutions there. And say if I paired them up correctly, say if I paired them up incorrectly, sorry. Say if I put the x value of 11 over 7 with the y value of minus 4, and the x value of minus 1 with the y value of 26 over 7, you'd get these two coordinates. And so you see that that's incorrect. It's not where they intersect. So just be very, very careful with that. That's a common error I've seen a lot, where you do all that hard work, you get the right values, and then just pair them up wrong at the end. No, make sure you definitely pair them up correctly. Right, so moving on, let's look at another case quick. So very similar scenario. We've got a non-linear and a linear. You always want to work these out the same way. So what we do, look at that linear equation. Let's make one of them the subject, the y or the x. Make one of them the subject to that equation. In this case, I'd make x the subject. It'll be easier. Avoid getting fractions and whatnot. Well, I take that value. I've now got x in terms of y. Let's substitute that into the second equation to eliminate the x dependence. And we now got an equation just of y. Again, expand, simplify, and collect like terms, and you're going to get a quadratic. And this will be what happens in most cases, because you remember when we was looking at those graphical interpretations, it intersects at 2 points. So you're going to get two solutions. Generally speaking, it's a quadratic equation that has two solutions, isn't it? So that's why we tend to get quadratics a lot. And we can just solve this in the way that we're familiar with. You might notice that this one, what I've done here is I've basically completed the square. You can use any method you see fit if you have multiple options. And if I, now rearrange this to solve for y, I essentially get these two solutions. And if I now substitute that y back in for x, I get these two solutions. So here's an example where you can compact your solution. So rather than having to have two solutions for y and two solutions for x, you can kind of put them together like this, where you have plus or minus and then a minus plus for the x. Like you see the minus plus switches around because when I substitute the y back into our equation at the top, you see it's getting multiplied by minus 4. So if I multiply by a negative sign, the plus becomes negative and the negative becomes plus. So plus minus turns into minus negative, turns into minus plus, sorry. So if you're comfortable doing that in that notation, that's a great way of, kind of saving yourself a bit of time and effort. If not, don't worry about it. Write out your two solutions. Y equals 1 plus 2 root 3. Y equals 1 minus 2 root 3. Substitute each one individually to find your two x values. And then just, make sure you paired them up correctly. But that's a handy little tip there if you're comfortable doing that. Right, let's look at one last case on the non-linear case before we look at the system of three variables. So this is a very common type of problem you might encounter where you've got two simultaneous equations, but there's an unknown constant. Like in this case, we've got k. And you'll be given an extra piece of information. Like here, you've been told that simultaneous equations have only one solution. Find the value of k based on that information. Okay, so what do we do here? So with a problem like this, what I would do is go ahead and try and find the solution to this equation anyway. And maybe we'll get a solution in terms of k, and then we could take it from there. So, okay, let's do the same thing we've been doing before. I'm going to make that first equation into a point that a form that I can substitute into the nonlinear equation. So I've made x the subject. I'm going to substitute that into my second equation like this. Now I need to expand and simplify like this. And then what we want to do is collect like terms. Well, k is just a constant. Y is our variable, our unknown that we're trying to solve for. So we want to collect like terms based on y. So we want a y squared term, we want a y term, we want a constant term. Essentially, you're going to produce a quadratic again, which we know is typically what's going to happen. And if we collect together like terms like that, you see we essentially get this. So it's basically just a quadratic again, but the coefficients are in terms of this unknown k. Now, we're told that this has only one solution. So it's kind of like that case that we saw earlier where what you might see here, what we've got is essentially a linear straight line, and we've got a circle, and it's basically a tangent to a circle. What does that mean in terms of this quadratic? Well, if there's only one solution to the pair of simultaneous equations, it means this quadratic is only going to have one solution. And what that means, we need to use something known as the discriminant. So you may or may not have heard of this before. This is something you should read up on because this is part of regular GCSE math syllabus. You should be familiar with it. But it is one of those more obscure topics that often gets overlooked, but it's really, really important. So first of all, let's identify our coefficients, of our quadratic. A, B, and C are basically equal to these little expressions of K. Having only one solution basically means this is true. So B squared minus 4AC, that should be sounding familiar, shouldn't it? It's basically what's inside the square root of the quadratic formula. So if you don't know the quadratic formula off the top of your head, you might want to look that up quick. Think about if that little expression inside the square root is 0. Well, it's the square root part that gets plus or minus, isn't it? That's what produces our two solutions. So if that is 0, that whole part disappears. You now don't have two solutions, you have one solution. So that's how we need to interpret that. When it says only one solution, what it means is that discriminant there, that little expression of b squared minus 4ac, is going to be 0. And we can use that to find out what k is. Because if we substitute in our little values for a, b, and c, you're basically going to get this. And if we expand and simplify, you get a simple little expression for k here, which if we divide by 4 and square root, you essentially get k equals plus or minus 3 root 2. So we know this, we're not actually interested in finding what that solution is to these equations. We're trying to find out what that value of k needs to be such that that this is only going to have one solution. So yeah, make sure you're comfortable with the discriminant. It can be used in many different ways. You might have even noticed I kind of set a problem that requires this in the previous lesson on exponential equations. So if you didn't know how to tackle that challenge problem, you might want to take another look at it. Maybe you'll know now based on this example. Right, so let's move on to the stuff that is exclusively part of the further GCSE math syllabus, which is when we have something like this, a system of 3 equations with 3 variables, linear equations though, only ever going to be linear. What do we do here? Now, you might be surprised. This might actually not seem as difficult as you'd first expect. We can solve this using just techniques of or probably elimination technique, but you could use substitution as well. We just have to use it more times in order to solve this. So let's say if I take the first 2 equations here and I want to eliminate one of the variables. Well, you might be able to see there, probably the easiest one there to eliminate would be the y. If I just simply add the 2. Because you see there, we're going to get a minus y and a plus y. It's going to cancel out and we simply get 2x plus 9z equals 17. Cool, we've eliminated the y there. Now what do we do? Well, if we could produce another equation of just x and z, well, we now have 2 equations of 2 variables. We know how to solve that. You've done that a million times before, probably. So can we do that? Well, yeah, because we used the first two equations. How about we now use the second and third equation? And again, this is important. You want to eliminate the same variable. So say if we eliminate the y here, how can we do that? Well, say if we do something like this. Do two lots of the first equation plus the second equation. And you see what you're going to end up getting there is a 2y minus 2y. It will cancel out. So I'm assuming you're already very familiar with this elimination method. And if we do all that, you see we're going to get 5x plus 14z equals 34. And there we go. So that is the key. That is the first tricky bit. And you'll find the rest of this, it will become very straightforward and familiar to you. That first step, we need to use two pairs of equations from that set of three to eliminate the same variable twice. And now you produce an equation, like a system of two equations with two unknowns. We know how to solve this. So you can work this out in any way you want. Let's say if I wanted to make the x values match, well, I'm going to times the top equation by 5 and the bottom equation by 2. And if I multiply through, you'll see it will produce this. And now the x terms match. So what I could do is I could just easily subtract those. And if I do, you see I eliminate the x. And now I've got 17z equals 17, so z equals 1. And that's it. Once you've worked out what one variable is, well, I can take that and just substitute that back into two of the original equations. So let's say if I take the first two equations again, but I'm going to substitute in z equals 1. Well, I basically get this, don't I? And if I rearrange these two equations by, getting the constants onto the right-hand side, so I get this essentially. Again, I've just got a set of two equations with two variables. This should be very straightforward to many of you. So if we solve this, maybe I add the two equations to eliminate the y and find out what the x is, and then you can substitute the y back to find out, substitute back the x, sorry, to find out what the y is. You can find out what those two values are from that little system there. And there we go. We now have our solution. So that first step is the important part. You need to produce two pairs of equations from that set of three and eliminate the same variable twice. And that's really important. So you're then producing now two equations with the same two unknowns, and then we can just solve as usual. And once you've got that first one, well, now the whole problem reduces down to just two unknowns, and we know how to do that already. So that's the trick. And you see that solution there. If you think back to that graphical interpretation of three surfaces intersecting one another, this is like a coordinate in three-dimensional space, like 4, 2, 1. That point in three-dimensional space where they will intersect. That's more just for your own interest, but you don't need to be aware of that for your exam. So there we go. So let's take a look at some applications now. Some cases where simultaneous equations can crop up, where you might not necessarily expect them to crop up. And it's a kind of question where it won't specifically say use simultaneous equations to solve this, but you need to be able to spot when we can use these techniques. So here we go. Let's look at an example like this question that we saw, not the same question, but the same kind of problem that we saw in the last lesson on exponentials. So conservationists tracking the number of endangered species over a decade. The initial number of animals now is unknown. So you might remember what that initial value was from the previous lesson, but let's imagine this time we don't know what that initial value is. All that we know is that they're growing exponentially over time, and that the count was 820 after 3 years, and then 2,461 at the end of the decade. So how can we determine how many there were initially? Well, let's produce our axes again like we did last time, population against time. Time in years, and we've got, say, these two coordinates. After 3 years, we had 820 animals. After 10 years, we had 2,461 animals. Well, we can't draw a straight line between it. It's not a linear relationship. We're told they're growing exponentially. So it's going to be an exponential relationship like this. So how do we determine what that equation is going to be? Well, just like with a linear equation, which is defined by two unknowns, like we have y equals mx plus c, the two unknowns we need to find are m and c. Well, an exponential equation is also quite simple, and it's defined by two unknowns a and r, or a and b. Sometimes we use b for the base of the exponential, don't we? But in this case, sometimes you use the letter r, stands for ratio. Like when you multiply by some common value over and over again, we often refer to that as a ratio. So I'm going to use the letter r here. So yes, you see there's those two unknowns we need to find. Well, we need two pieces of information to find those unknowns. And that's what we have here, these two coordinates. But how? How can we use that to solve what those two unknowns are? Well, if we substitute in those two coordinates, so we know at 3 years, the population is 820. After 10 years, the population is 2,461. And we produce these two equations of two unknowns. We can solve this simultaneously. But how? Notice in this case, we can't just do an addition or subtraction of the two, but we want to use the same idea of eliminating one of the variables by combining the equations together. How can we do that? Well, notice that a is multiplying the r to some power. Well, if we do a division like this, that will cancel out the a. That will eliminate the a. And the r over 10 to the r over divided by r over 3 will just get r to the power 7, won't it? And you see what we've done there? We've eliminated one of the variables. And now we can solve for r, like in the same way we did last time, where we have to now take the 7th root of this fraction. And what you find is you get 1.17, the same value we got last time. So that's telling us that the population is increasing by 17% each year. Now that we've worked out one, we can always substitute back into one of our equations. Like, let's say if I substitute into the one after 3 years. So a times by 1.17 to the power 3 will get us our population of 820. Well, if I divide both sides by 1.17 to the power 3, you're going to find out what a is. And remember, a is where it intercepts the y-axis, basically the initial value of this population growth. And we see that's 512, the same as what we got last time, which is should happen. Right. So there we go. That's like a callback to the question we had last time, but different this time, where we didn't know the initial value. What we've been given is two kind of arbitrary points, and we want to work our way back. And you see there, it essentially boils down to a simultaneous equations problem that we have to solve in a unique way. Let's look at one last problem. A bit of a trickier problem that involves using cubic equations. So let's say if we have something like this. So we've got this factorized form of this cubic polynomial. And we know it's of this form, ax plus b times x plus 4 times x plus c. And it produces this cubic polynomial. And we want to use this to try and find out what a, b, and c are, where we're told they're integers. How would we do this? Well, to solve something like this, we can use a really valuable technique, which is basically equating coefficients of, like when we get two equations that are equal to each other of the same form, we can then set their coefficients equal to one another. So let me show you how this would work. So first things first, what we want to do is expand out that factorization on the left-hand side. So expanding out triple brackets like that, yeah, we've got some unknown constants in there, but we want to expand, simplify, and collect together like terms of x squared, and x cubed, and of course our constant term. So you might want to pause here and try and do that yourself. That should be something you'd be quite comfortable doing now after our lesson on cubic equations. You just got to be mindful of those unknown coefficients, those unknown constants there. But yeah, if you want to give that a go, do so now. Otherwise, let me show you how we would do that. So if you remember back to our lesson on cubic polynomials, what we would do is expand two brackets first. And if we expand this out in the usual way, you'll get this. And now what we want to do is collect together like terms. So we've got the x squared term at one end. We've got 4b, which is our constant term. But then we've got two x terms in the middle. If we bring those together, you'll get a coefficient of 4a plus b. There we go. So we've expanded that one out and you produce this quadratic with coefficients in terms of a and b. Now, what we want to do is take that and expand that by with the final factor of x plus c. And so we now need to multiply that through. So multiply each of the terms of our quadratic by x, multiply each one by c, collect together like terms. So you're going to essentially get this. So it looks big and complicated, but it's not using anything that we don't already know. It's just a lot of working out. You need to be comfortable with doing things like this. So in further GCSE math, and certainly for you guys who might be going on for A-level math, you're going to start getting much bigger calculations like this. You need to be comfortable with doing something like this, collecting together like terms. So you see we collect together all the x cubed terms, the x squared terms, the x terms, and then finally the constant at the end. And we get this one big quadratic, not quadratic, sorry, it's a cubic polynomial. And we know that is equal to, the cubic polynomial was given at the start, 2x cubed plus 19x squared plus 49x plus 20. So this is where we're at now. What can we do here? This is where we can, use that technique I mentioned, where you equate coefficients. So you see here, we've got one cubic polynomial with unknown coefficients in terms of a, b, and c. And then we have another cubic polynomial with, just numbers for coefficients. Well, we can then equate those coefficients. So we know the coefficient of the x cubed terms are going to be the same. The coefficients of the x squared terms are going to be the same. The coefficients of the x terms will be the same. And then those two constants on the end, 4b, c, and 20 will be the same. And it allows us to produce a little system of equations like this that we can now solve. So make sure, you're comfortable with that. Maybe pause in and take a look at that, and you can clearly see what we've done there, where we've equated the coefficients of the appropriate powers of x. Now it's a matter of just solving this system. So let's say if we number those equations for simplicity. Well, the first one is very nice, isn't it? It's just telling us that a is equal to 2. Great. Well, let's substitute that into equations 2 and 3. Because there's an a that's in equation 2, isn't it? So if we put a equals 2, we get this. Put a equals 2 into equation 3, we get this. So now, see what simplifications we can make. Not much, but equation 4, look, we can divide by 4, can't we? And we get BC equals 5. All right, where do we go from here? Well, let's say if we look at that first equation over there that we produced, we could rearrange this to get it into the usual form that we're familiar with for simultaneous equations. Maybe that second equation as well. But notice there what I've done. I've eliminated that BC term because we know BC equals 5. So I just put in 5. And again, let's rearrange it to get it into its usual form. And you notice we've run into a bit of a problem here. They both produce the same equation. So we can't actually solve this, because it's the same equation, it's the same piece of information, it's not going to help us. So all we've got is this one equation, 2c plus b equals 11. And don't forget, we've still got equation 4, bc equals 5. So that's what we need to now use to try and solve for b and c. We already know what a is. So what can we do there? Well, if we want to substitute one into the other, let's produce a bc term in this new equation we've got. So say if I times through by c, I'm going to produce a bc term. And if I now substitute in that bc equals 5, and doing a little bit of rearrangement, you're going to get this. So we've eliminated that bc term, but more specifically, what we've done, we've eliminated b. So you see, it's the same idea that you're familiar with, like where we're trying to eliminate a variable to produce an equation of only one variable that we can then solve. But you see, in more complicated scenarios, we have to get a bit more inventive about how we eliminate a variable. But it's the same idea. We want to eliminate an unknown. So we produce an equation like this quadratic equation here, but there's only one unknown, it's c. So we can just solve this quadratic and find out what c is. And you might notice you can factorize it like this, and you'll get two solutions. You'll get c equals 5, and you'll get c equals a half. However, the only valid solution there is c equals 5, because remember at the start, we was told a, b, and c are integers. You can see that up in the top right. So half is not a valid solution. So we get c equals 5, and now, well, we know that bc is equal to 5, so therefore b must be 1. And there we go. We've managed to solve that. So you see here, a question here on cubic, like it looks like it's a cubic equation problem. It's actually a simultaneous equations problem, or more specifically, even a problem with three unknowns, a, b, and c. And by using that technique of comparing coefficients, once we get two cubic polynomials in the same form, we produce those equations, and then we use our simultaneous equations techniques to solve. But that's quite a tricky problem there. So well done if you can follow that. But yeah, like I said, same idea of like eliminating and substituting, but sometimes you need to get a little bit more creative. Right, so let me leave you with a challenge question here. So take a look at this system of three variables and three equations. Try and solve this. What you'll find is you'll get an unusual solution. And can you interpret what it means? Perhaps not graphically, because like I was saying, it's this is going to produce like a three-dimensional graph, and you might not want to do that. So you might want to consider this system, which it's just two variables. So you could plot this on a set of axes, x and y, and see what happens, or and try and solve this pair of simultaneous equations. And you'll run into a similar unusual solution. Yeah, and I want to see, can you interpret what that means? You should be able to interpret in that system of two equations, and see if you can then use that understanding to understand what's going on in that system of three equations. So I'd recommend everyone give that a go, because this is one that many of you should be able to take a good stab at. But that's it for today, and that's it for algebra now. So we've done a lot of lessons, 6 lessons on algebra, learning all kinds of new algebra techniques, because algebra is so important. It's used in so many different ways. Next time we're moving on to a completely new topic you've probably never seen before. It's not part of the regular GCSE syllabus at all, and that is calculus. More specifically, we're going to be looking at differentiation. There's two aspects of calculus: differentiation, integration. We don't look at integration at all at GCSE level, so we're just focusing on differentiation, which is all about gradients and rates of change. So yeah, let's leave it there. Make sure you go through that checklist. You can tick everything off, that you understand all those key things you need to know. And yeah, I'll see you next time for some calculus.